derivative. Okay, this today I will start with the high order of derivative. Okay, please refer to page this page to page 6 of part B. I will explain again. I will explain again what is a derivative, what dy dx. Okay, for today I will start with the high order of derivative. Before that, let's say we have this example, this function. Okay, I will show you by using the Microsoft, by using the whiteboard. Okay, for example, let's say we have where's my part B? Mm, okay, high order of derivative. Let's say we have this function y or fx equal to 6x to the power of 3 minus 12x squared minus 6x minus 2. Okay, based on the rule of differentiation, the first derivative of the there is the first differentiation, first derivative of y prime or f prime x or dy dx. This is the first derivative. Based on the rule of differentiation, this is equal to 18x to the power of 2 minus 24x plus 6. That is the first derivative, y prime or f prime or dy dx. And then beside the first derivative, we can also find the second derivative. We call it as a second derivative. That is y double prime or f double prime x or d squared y dx squared. What does it mean? The second derivative is the derivative of the first derivative. Okay, based on the first derivative. Okay, now we can also apply the rule of derivative. So since the first derivative is 80x squared minus 24x plus 6, so the second derivative is now equal to 18 times 2 is 36x to the power of 2 minus 1 to the power of 1 minus 24 plus 0 or minus 24. That's the second derivative. And so on. We can also find the third derivative. Pembezaan darjah ketiga. Third derivative. It's y triple prime or f triple prime x or d to the power of 3 y over dx to the power of 3. There is the third derivative. So the third derivative is the first derivative of second derivative. So since the second derivative is 36 minus 24, so the third derivative is equal to 36. And then so on. We can find the fourth derivative, fifth derivative, and then there is depend on the question. What is the purpose to take the high order of derivative? Is depend on the purpose. Maybe you need to follow what is maybe the question asks you to find the fourth derivative, third derivative, fifth derivative, and so on. And then you need to find the derivative step by step. Okay, from the example, the fourth derivative, pembezaan darjah keempat. The fourth derivative now is y to the power of 4 equal f 4x equal to d to the power of 4y dx 4. So this is since the third derivative is constant, the fourth derivative is equal 0, and so on. We can also continue to find the fifth, sixth, and so on high order of derivative is depend on the situation, whether we need the first or second derivative. But for this class, our focus is for first and second derivative. In economic, we can apply this concept, the first derivative and the second derivative, in order to find the extreme value, nilai extreme, maximum, minimum, and so on, based on the economic theory. Okay, then the next part, okay, based on this concept, second derivative, third derivative, and so on. Now we move to the sections. Section 3, part C of the topic. It's about the optimization. Function with a single variable. We need to in terms of application, we need to find the what we call it as the extreme value, nilai extreme. What we call it as a extreme value. The extreme value or relative extrema. This extreme value is referred to the maximum and minimum. Maximum and minimum. That's about the extreme value. Nilai extreme can be divided into the maximum or minimum. Maximum or minimum. And that is the extreme value. Okay, how to determine the extreme value? Okay, if you refer to page part C, page 1 and page 2. Okay, again I will explain again about the extreme value. Before that, last week I explained about the slope of the tangent line. Okay, the first derivative, the value of the first derivative, nilai pembezaan pertama, the value can be positive. The value of the first derivative can be positive or negative. The first derivative f prime x negative, or the first derivative can also, the value of the first derivative can also equal 0. This value is also known as the slope of the tangent line. So the slope of the tangent line can be positive, negative, or equal 0. It depends on the function, whether the function is what we call it, whether the function is positive or whether the function is increasing or decreasing. So in other words, if the first derivative is positive, the slope of the tangent line is also positive, like figure A and B. The slope of the tangent line is also positive. That show the function is increasing when the slope of the tangent line or the first derivative is positive. The slope is increasing, like this one. The slope is increasing. But when the first derivative is negative, this negative show that the slope of the tangent line is negative. In other words, the function is decreasing, menurun. Fungsi semakin berkurangan, decreasing, or fungsi semakin meningkat, increasing. Okay, now that is based on the value of the dy dx. The value of the dy dx, whether the value is positive, negative, or equal 0. Based on this concept, positive, negative, and 0, we can determine whether the function is increasing or decreasing. Okay, that is the first scenario you need to know in terms of slope of tangent line. Now we are going to apply the first derivative in terms of slope. What slope? The slope is referred to the slope of tangent line. That is the dy dx. Okay, the second derivative The second derivative will be used to refer to the concavity. Concavity adalah kecekungan or kecembungan. Kecekungan. There are two situations here: concave up or concave down. Concave up or concave down. Concave up, there's a cekung ke atas. Cekung ke atas. Cekung ke atas. Like this one, like U. Like a U shape, cekung ke atas. Concave down is cekung ke bawah. Cekung ke bawah. The graph like N, cekung ke bawah. Now we have two types of concavity. Cekung ke atas, concave up or concave down. So how to determine, how to know, how to decide, how to label whether the graph is concave up or concave down. Macam mana nak tentukan fungsi tersebut cekung ke atas ataupun cekung ke bawah. So we can apply the second derivative of the function based on the second derivative of the function. So based on, as we can see here, if the second derivative is positive, okay, if the second derivative is positive, f double prime is greater than 0. The graph, we can conclude that the graph is concave up, or the graph is cekung ke atas. But if the function is, the second derivative is negative, the graph is concave down, cekung ke bawah. That's the concept that you need to know. How to apply the dy dx, the second derivative of function in terms of concavity. So if the value of, if the second derivative, the value of the second derivative is positive, the graph is concave out. Otherwise, when the value of the second derivative is negative, the graph is concave down. We can apply this concept in order to find whether the graph is concave up or concave down. That's why we have this function. Okay, as you can see here, okay, this is a concave down. And then the graph in page 3, there is a concave up. Cekung ke atas. As you can see here, this is the graph. The first part, the first derivative, before we have the slope is changed from the negative to positive. So we can conclude that the graph is the first area, and in the first area the graph is decreasing. After that the graph will increasing. For concave, this concave up. For concave down, we can see here the slope of the graph change from the positive to the negative. So based on this question, we can conclude that this graph is concave down, cekung ke bawah. Perubahan fungsi, perubahan kecunan daripada positif pada negatif. Okay, that for this topic, we can I hope you can pay attention here. The first derivative generally refer to the, in general, we can say that the first derivative normally is refer to the slope of tangent line. But meanwhile, the second derivative is also normally is referred to the concavity, whether the graph is concave up or concave down, based on the value of the second derivative. If the value of the second derivative is positive, the graph is concave up. So when the value of the value of second derivative is negative, the graph is concave down. That's how to apply first derivative and second derivative. Okay. Now please refer to page 5. Now we can apply these two concepts. These two concepts of concavity, the first derivative and also the concavity. Please refer to this graph page. I think this is page 4. Sorry, page 5. I will explain how to read this figure. How to read this figure. Okay. As you can see here, okay, now let's say I just draw this graph randomly. When I move from x1 to for negative on the left to the right. Let's say I move from the left to x1, x1 to x2, x2 and x3, and x3 to the positive infinity. As you can see here, what happened to the uh, function when we move from left to the right? You can see here the function is increasing, fungsi meningkat until x1. After x1, the function is decreasing, berkurangan. After x2, again, the graph increasing, and after x3, p3 or x3, the graph decreasing. And now we can see the movement of the graph when we move from the left to the right, from negative infinity to positive infinity. So, okay, now let's see, I move to x1. Move to x1. As you can see, when the value of x increase by 1 unit, or maybe from negative to positive x1, but we can see here the value of the function is increasing. The value of the function is increasing. The value of y. If x increase, y also increase. Meaning that there is a positive relationship, or the slope of the function is positive, or the second derivative is also sorry, the first derivative is also positive. Remember, I hope you can still remember, the first derivative is also known as the slope of the tangent line, or the slope of a linear, of a straight line. Okay, after x2, when I move from x1 to x2, you can see here the value of the function y will decrease. Meaning, show that this proves that the first derivative in this area is negative. When we move from x1 to x3, actually x1 to x2, the slope of the first derivative, or the slope of the function, is negative. Now, when we move from x1, in other words, when we move from x1 to x2, the function is decreasing. Function is decreasing. Now, and then we move from x2 to x3. So we move from x2 to x3, but we can see here the value of y. The function started to increase. The value of y is increasing when we move from x2 to x3. In other words, between x1 and x3, the first derivative, the slope of the function, must be positive. We can determine the sign of the function, whether positive, negative, by only use the concept of differentiation. We need just the we need the one. We just need to determine the value of x, and then we can find whether the function is increasing or decreasing. The function is decreasing, meaning that the slope of the tangent line is positive. The value of the first derivative is positive. When the function is increasing, semakin berkurangan, nilai dia semakin berkurangan, menunjukkan, show that the first derivative is negative, when x increase from x1 to x2, the value of the function is decreasing. In other words, we can conclude that from x1 to x2, the function is decreasing. And then when we move from x2 to x3, when we move to x2 to x3, what we can see here, the function now increasing again. In other words, the first derivative is positive, and so on. After x3, now we can see the function. In this case, the slope of the function, cannot be defined. But for this case, our focus is we like to focus on the situation where, for example, from 0 to x1, x1 to x3, x2, and x2 to x3. We will focus on the in terms of first derivative and second derivative. Okay. Now, please, before this, I explained about the before x1, after x1, before x2, after x2, and so on. But now I would like to look into the what happened at x1 at this point. This point is very important. For example, x1 and x2. Before x1, we can see here, before x1, the function is increasing. The function is increasing before x1. After x1, the function is decreasing. Okay, at x1, so in other words, when we move from when x move to x1, to after x1, we can conclude here the slope of the tangent line is positive before x1. That's why when x increase, x increase to x1, y also increase because the slope is positive. Between us, before x1, the function is increasing, meaning that the slope of the tangent line is positive. That's why I write here first derivative of x is positive. In other words, the slope of the tangent line is also positive. After x1, you can see the slope of the tangent line is the line is decreasing, meaning that the slope of the tangent line is also negative. So the first derivative in this area is negative. Okay, again, after x2, when we move from x2 to x3, we can see the function is increasing. In other words, the slope of the tangent line is positive. The sign of the slope changed from the positive to from negative to positive. Okay, now that is the situation before and after x1, x2, and x3. So now we want to identify what happened at x1. What is the what is the slope of the tangent line at x1 and x2, for example? Okay, at x1, before x1, the slope is positive. After x1, the slope is negative. Now, x1 is also known as the critical point or turning point. Same goes to the x2 and also x3. But for the class, we only focus on x1 and x1 and x2. Okay, at this critical point refer to the point where the sign of the slope is different. Sebelum nak lepas that critical point. Sebelum critical point, the slope positive. Selepas critical point, the slope the nilai keturunan adalah negatif. There is a change in the absolute value of there is change in the value of tangent line, a value of the slope of the tangent line. But we want just our focus is before and after this tangent line. So for this example, we assume that x1, x2, x3 is a critical point, but our focus is more on the x1 and x2. So now at this point, what happened at this point? The first derivative is, let's say at x1, the first derivative is 0. The value of the slope is 0. the value of the tangent line is 0. That's why we can draw one line here. As you can see, we can draw the horizontal line. The horizontal line, the slope is equal to 0. Okay, the first derivative is 0. The second derivative, I will show you the calculation later. But now I just explain the concept. At this point, like at x1, the first derivative is 0, but the second derivative is negative 0. That happened at point x1. So in this case, the graph is concave down at this point. Concave down. Meaning that the graph is a cekung ke bawah. When we move from the left to the right, you can see here the graph is cekung ke bawah. Concave down. I draw the graph, I highlight the graph in a green color. We can see that the graph is concave down. So the extreme value, okay, this extreme value is a maximum value. Remember, the extreme value can be divided into the the extreme value can be divided into the maximum and minimum value. So in terms of second derivative, the value of the second derivative in this case is negative. The second derivative is negative. So for this case, I hope you must remember this this concept. At the critical point x1, in this case, the x1, the first derivative is 0, the second derivative is negative. We can conclude that the critical point is the maximum point, maximum relative point. That's we just want to know whether the graph is there is a minimum or maximum. In this case, we can say that this minimum, maximum relative compared to other value. Now we move to the P2. We move to the P2. We have a P2 here. After P2, before P2, the slope is negative. The slope is negative. After P2, the slope is positive. Pfx is positive after x2. The slope is positive. Now we can see that the change of the slope from negative to positive. From negative to positive. Based on this concept, we can conclude that the critical point, we still have the critical point here, x2. This critical point is a minimum relative point. Minimum relative. So at this point, the first derivative is 0. The second derivative, the first derivative is 0. The second derivative must be positive. So we can conclude that this graph, because before the critical point, the slope is positive. After critical point, the slope is before critical point, the slope is negative. After critical point, the slope is positive. Or before x1, the slope is decreasing. After x1, the slope is increasing. The slope is moved from the increasing to decreasing. We can conclude that at that point, the point is a minimum point, or the extreme point is also known as a minimum point. Okay. In addition, we can also see here the second derivative of the function is positive. To show that at that the critical point is a minimum point, minimum relative point compared to other point. Okay, that's how we can apply. We can apply the concept of maximum, minimum. Okay, for example, if you refer to page 7, that is how to determine the relative extreme point. 7, how to determine the relative extreme point. I will show you step by step how to determine whether the point is negative of the point is positive point or negative point. By only use the this by only use this step, we can find, we can detect, we can conclude what is the type of whether the slope of the function is the slope of the function is at a maximum or minimum. I will show you one by one. And in the next example. But please remember this two situation here. As I said here, for maximum, the first derivative is positive. Or we can conclude here, if the first derivative is positive, but the second derivative, in this case, the second derivative is sorry, the first derivative is 0. The first derivative is 0, but now the second derivative is negative. So we can conclude that the maximum point is a relative, this occur at the maximum relative point. Maximum relative point. The first, because the graph is concave down. The graph is concave down. The second condition is the first derivative is 0, but the second derivative is positive. Now we can, for this case, the critical point is a minimum relative point. Minimum relative point. So for this topic, you need to know this. For this situation, the first derivative 0, the second derivative is positive or negative. The first derivative will determine the slope of the tangent line. The second derivative will determine the concavity, whether the graph is concave up or concave down. If the second derivative is negative, the graph is concave down. If the second derivative is positive, the graph is concave up. The graph is concave up. So I will show you the, okay, for example, let's see. Please refer to page 8. Please refer to page 8, how to find the relative extreme point. Let's say, please refer to page 8. Given in the question is, let's say we have fx equal to 3x squared plus 2x minus plus 2x minus 3. 2x minus 3. Let's say we have this example. Now I would like to determine the relative, let's say I want to find the increasing, find the area where the function is increasing or decreasing. Find the area where the function is increasing or decreasing. Increasing or menaik atau menurun. CREA, increasing or decreasing. Now find the range where the function is increasing and also the function is decreasing. Now we need to know the critical point. So in order to answer this question, okay, the first part we need to know the critical point. Find the critical point first. Find the critical point. What at this point, the first derivative is always equal 0. Okay, that's all. the point is also called as a critical point because at that point the first derivative is 0. So the first step, we need to take the first derivative. The first derivative of this function is equal to the first f prime x. F prime x equal to 6x plus 2 and equal 0. 6x plus 2 and equal 0. So we know that x equal to negative 2 over 3 or negative 1 over 3. Okay, this is the critical point. This is a critical point uh, uh, for x. When x equal to negative 1 over 3, the function reach the critical point. Okay, that's about uh, the critical point. So what critical point? Okay, critical point. Remember, also is a coordinate point. Is one of the coordinate point belong to the equation. So we need to know x and y. For this case, we know x equal to negative 1 over 3 and then y is y. In order to know y, we just substitute x equal negative 1 over 3 into the equation. That is 3x 1 over 3 to the power of 2 plus 2x 1 over 3 uh, 2x minus 3. We just substitute this critical point in the equation. We find that at this critical point, the value of y, f negative 1 over 3, the value is y is negative 10 over 3. So at the critical point occur at point x equal negative x equal negative 1 over 3 and y equal to negative 10 over 3. That is the critical point. Okay. So we know the critical point occur when x equals negative 1 over 3 and y equal to negative 10 over 3. At this critical point, the the first derivative, negative 1 over 3 is equal 0. That is the value of y. This y, not the slope. This y. But the slope of the function is negative 3. Now, for example, let's say if I draw the line, I have this critical point, negative 1 over 3 for x. Now I want to determine what happened. I want to know whether the function is increasing or decreasing before and after the critical point. So I need to find the slope of the tangent line. The slope of the tangent line before the critical point and after this critical point. F prime n. In other words, we need to find the value of the first derivative. So in other words, how to determine the slope of the tangent line, whether the slope is positive or negative. First, we need to choose any number of x, but the value is less than negative 1 over 3. Negative 1 over 3. For example, let's say I choose negative 2. You can choose any number as long as the value is less than negative 1 over 3. So the slope of the tangent line when x equal to negative 2, based on the first derivative, we know that the first derivative is 6 times negative 2 minus plus 2. You can see here the answer is negative 12 plus 2. This is a negative 10. So we know that before this critical point, the slope of the tangent line is negative. The slope of the tangent line is negative. Okay, after the tangent line. Okay, after the tangent line. Now we need to determine the slope of the tangent line after negative 1 over 3, because this is a critical point. X equal to negative 1 over 3. This is a critical point. This is a critical point. This is a critical point. Okay, now I would like to choose any number that greater than negative 1 over 3. Let's say I choose 10. I choose a 0. So the slope of the tangent line f prime 0 equal to 6 times 0 plus 2. The answer is 2. So after x equal, after the tangent line, the slope of the tangent line is positive. Now we can see here the graph. Based on this graph, the slope of the tangent line. The slope of the tangent line the slope is of the tangent line, the sign of the slope of the tangent line change from the positive to negative. Okay, this negative and positive change from the negative to positive. In other words, this negative show that the function is decreasing before negative 3 and increasing after negative 1 over 3. Increasing before tangent line, the function is decreasing. After tangent line, the function is increasing. Okay. Oh my God. Yes, here the function is decreasing, and after the tangent line, the function is increasing. So the critical point is x equal negative 1 over 3 and y equal to negative 10 over 3. That's how to find whether the function is increasing or decreasing by using the first derivative. Then we can see here this function has a negative slope. The slope is changed from positive. The slope is changed from negative to positive. So based on this, based on the situation, we can see here the graph. At the first part, the graph is decreasing, and then after that, at the end of the positive infinity, when we move to the positive infinity, we can see that the graph is increasing after the critical point. So the slope change from negative to positive. For this case, we can conclude that the graph is concave up. So the critical point, negative 1 over 3 and 0 over 3 is a relative maximum, because we still don't this is a relative maximum at this point. And then the second derivative, the first derivative, we can check by using the second derivative. The first derivative is 6x plus 2. So the second derivative is positive 6. It's always positive. So we can conclude here, if we refer to the previous example, when the second derivative is positive, the graph is concave up. So the critical point is a minimum point. It's a minimum point or relative minimum point. So we can conclude that the relative minimum point is, for this function, the relative minimum is negative 1 over 3 and positive 10 over 3. That is the concept of the first derivative and second derivative in order to determine the concavity or the maximum or minimum value. Okay, this example is referred to the quadratic equation. Okay, I will show you. If you draw this graph, okay, let's say I would like to draw this graph to prove this statement. We have the critical point. This graph at the critical point at x equal -1/3. The graph is increasing before -1/3 and decreasing after 1/3. Okay, if I share with you, as you can see here, let's say when we draw this graph, for example. Okay, I will show you the drawing. Please wait for a few minutes. Okay, I will show you how to draw this. Okay, let's say, how about the, okay, I will draw the graph. Okay, by using a Desmos here. Okay, please wait. We have y equal to uh 3x to the power of 2 plus 2x plus 3 plus 3. Okay. Uh, -0 3x plus 2x minus 3. Sorry, minus 3. Here we show you the graph. How to copy. Okay, I will show you the graph for this function. For this quadratic function. Okay. Yes, you can see here. Okay, this graph for I hope you can see this graph. Okay, this is a y equal to yeah, okay, this graph for is y equal to 3x squared plus 2x minus 3. Okay, there is the graph. We have this point here. Okay, in quadratic we call it as a vertex point. This is a vertex point. Okay, the point is this -1/3, and then the second one is 10 -10 divide by 3. Before this vertex point or critical point, the slope of the tangent line is negative. If you choose any point before the before the critical point, you can have you can prove that we can prove that the slope is negative because the function is decreasing. After x equal -1/3, if you choose any point, you will find that the slope of the tangent line f prime is positive. So we can conclude that the function is decreasing before from -infinity until -1/3, fx is decreasing. Uh, between -1/3 until positive infinity, fx is increasing. Fx is increasing. And then at the first derivative of -1/3 is 0. The second derivative, -1/3, is positive. We have proved. We have just proved this. This formula is a positive. Is a positive to conclude that the graph is concave. Concave up with the minimum point is a -1/3 and negative 10 over 3. That's how we can apply the dy dx, the first derivative and second derivative, in order to determine the uh, 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 in order to determine the area where the function is increasing or decreasing, and at the same time we can also determine the critical point for the function. Okay, that's one of the example that's related to the critical point. Okay, when we're talking about the critical point, that refer to the maximum or minimum point. Okay, any questions so far? Is everything okay? Any question? Please, can somebody please respond?
No, doctor.
No question. Okay, if you have no question, I think we take a break for 15 minutes. Can we take a break? We continue at 4:15. I will proceed to the next example. Can we take a break?
Yes, doctor.
Okay, we take a break. Please respond. We take a break for 15 minutes, right?